of g of x and consider the limit as x approaches 1 from the right side of g of x as well. So looking at this graph, we're approaching 1 from the left side. We're approaching our function values this way, and we're going to approach 2. And approaching 1 from the right-hand side means we're going to be approaching the value of 1. And so what is the limit as x approaches 1 of g of x? Does not exist. Again, they're going to 2 different values, which means our limit overall cannot exist. Now, a slightly different question here. What is the limit as x approaches -1? Well, -1 is over here. And -1 is just approaching the single curve. It's not where this crazy change is happening. It's just approaching on this first curve. And so if I'm plugging in just -1 here, 3 times -1 minus -1 cubed. 3 times -1 is -3, and -1 cubed is -1. So that's going to be -3 plus 1, which is -2. So right here is this point, -1, -2. As I approach from the left of -1, we're approaching -2. And as I approach from the right side, we're also approaching -2. And so because this value at -1 isn't where this crazy change is happening, it's a little bit easier. All right, so we've seen a couple examples where the limits do not exist. And so we want to look at a couple more examples. Here, example 3, evaluate the limits. And again, if you have a graphical understanding of what's happening, then these things can be very, very easy. So let's look at this graph. Hopefully you know what this looks like. Kind of interesting. Remember, x over x is almost 1, right? It almost reduces to 1. And they differ just by the sign, because this is always positive and the denominator is going to change. So I'm going to go and put in my absolute value of x divided by x and take a look at that graph. I'm going to do a zoom decimal, zoom 4. It just sort of zooms in a little bit. And you can see that we have this graph is negative when x is less than 0. It has a value of 1, -1, and it has a value of +1 when x is greater than 0. What happens at 0? You'll notice I used open circles. It is undefined, defined, at x equals 0. Remember, denominator domain, that x is not allowed to be 0. And so it's actually got 2 undefined values here. If we were to ask, what is f of 0? F of 0 is undefined. And that's really important to remember, denominator domain. Okay, so again, what is the limit as x approaches 0? So that's here at 0 of the function. So we want to consider what is the limit as x approaches 0 from the left, and what is the limit as x approaches 0 from the right of f of x. So as we're coming in from the left side, our output values are all -1. And when we're approaching from the right side of 0, our output values are all +1. All positive, all -1. So this limit is another example of a limit that does not exist. So we're approaching different outputs from the left and the right. Here we have g of x is 1 over x squared. Again, a graphical understanding. 1 over x squared. It's really useful. So it's an interesting kind of graph. And again, it's important to think about, hey, what's going on in this graph? Again, x squared cannot equal 0, which means x cannot equal 0. It is undefined. There is what we would call a vertical asymptote at x equals 0 in this case. And if we wanted to ask, hey, what is the limit as x approaches 0 of this function? Well, we could say, again, considering what happens as we approach from the left of our function and as we approach 0 from the right of our function. As we're approaching from the left of 0, our function is going way up. It's getting huge. It's getting super big. It's growing to infinity. And as we approach from the right side of 0, again, our function is going up again, getting super huge and approaching positive infinity. Now, they match. However, infinity is not a number. It is not a number like 3 or 4 or 12 or pi. It is an idea. It is a theory. And because it doesn't actually approach a value, infinity just keeps getting bigger. If we moved infinitely closer, we'd still get a larger value. It's not a constant value that doesn't change. Infinity keeps on going. So we can't actually say there is a limit here. Again, this is an example of a limit that does not exist. However, that's at 0 because this crazy weirdness is happening at 0. What happens if I said, well, what's the limit when x is 1? Well, that's a very different thing. Here's where x is 1, and there's an output there. Well, let's see. What's g of 1? G of 1 is going to be 1 over 1 squared, which is 1. So this has an ordered pair 1, 1. And if I want to consider the limit, as I approach 1 from the left, our function approaches the output of 1. And as I approach 1 from the right, our function gets closer to 1. So that limit does exist. We need to look out for vertical asymptotes. Okay, so something to keep an eye out. So example 4, evaluate the limits. Again, if we have this graphical understanding of limits, then if I can think about the graph or use the graph to help, then that's a great thing that we could do here. I know, for instance, that this function, 3x squared minus 4, is a parabola, and I know that it has a y-intercept of -4, and I know it's an up parabola. I don't know exactly what it looks like, but I know it's a nice, smooth curve, and if I wanted to graph it, I could. Look something like that. There we go. All right. And so if we wanted to know, hey, what is the limit as x approaches 3? Well, we know this is a nice smooth curve. So as we approach 3 from the left, we're getting closer to some output value. And as we approach 3 from the right, we're coming down towards some output value. So there's nothing weird going on. So do you think that perhaps if I wanted to find the limit as x approaches 3 of this function, perhaps I just need to figure out what the output value is by plugging it in. Let's just plug in the 3. And that's 9 times 3 is 27, minus 4 is 23. I think so. So yep, 23. So there it is. It approaches 23. So if you don't have anything weird happening, then we know that we can just sort of do what's called direct substitution, where we can just plug in our x value. That's kind of nice. Here's a crazy function. So let's look at this graph. It's crazy. When you plug this into your calculator, again, make sure you put parentheses around the numerator and around the denominator. X squared plus x in the numerator divided by x plus 1 in the denominator. Oh, look, there's a hole in this graph. Interesting. It looks just like a line, except there is a hole right here. Very, very interesting. Wonder where that comes from. All right, so there is a hole in this graph. Very cool. But we're interested in what's happening around 1, not over here, which is occurring at -1. Again, denominator domain, we know x cannot equal -1. Denominator domain, that's where the hole is. And so we're interested in know what's happening over here. Well, over here, it's pretty easy to see. I'm just going to use trace. And at 1, the output is 1. So the limit as x approaches 1 from the left has an output of 1, and from the right has an output of 1. So the limit is just 1. Same understanding here. We know cosine, high, middle, low, middle, high. And this just happens twice as fast. So we have a nice smooth curve. And again, there's nothing weird going on. And we just need to see what happens at pi over 3. So I'm just going to go ahead and plug that in. The limit as x approaches pi over 3 of cosine of 2x is just plugging in pi over 3. And you could use your calculator if you wanted to, but cosine of 2 pi over 3, looking at your unit circle, 1 pi over 3, 2 pi over 3 is right here. And that ordered pair, short leg, long leg, -1/2, radical 3 over 2. Here is the cosine value, -1/2. My drawing was clearly not accurate, but that's okay. So this one, -1/2. So sometimes direct substitution is really easy to do. We'll talk more about that coming up. There you go, ladies and gentlemen. Remember, to have a limit, the limit from the left needs to match the limit from the right side of the x value.